Okay, here we're going to look at binary search trees, which are referred to as BSTs, and we're going to focus on the vocabulary associated with binary search trees and really the internal guts of what makes something a binary search tree. And I want to draw your attention to this important piece, which is in introductory CS classes, we often are programming to learn to program, and the further along you get into an undergraduate degree in computer science, you start writing code to better understand an algorithm. So you're not writing code to try and learn to program. You already basically know how to program, but then you're just using those skills to really dig deeply to understand how that algorithm works. And here we're going to look at the data structure by a binary search tree. We're going to go over some key vocab and some key learning goals, and you'll see those on the later slides. Okay, so here's a binary search tree, and I just want you to pause and observe what it has in it, and see if you notice any patterns. And binary search trees are going to be representing often a map or a dictionary, so that's something associating a key with a value. So that might be something like a name associated with a phone number. But in our picture here, we're only going to be showing the keys, and the keys are just numbers. That'll make it easier for us to see how these binary search trees or these BSTs are structured. So did you notice that for any circle, those we're going to call nodes, for any node, all the nodes to its left were smaller than it, and all the nodes to its right were bigger than it. Did you also notice that there were no duplicates? And that each one of these nodes had either 1, 2, or 0 children. And children is the name that we use for these. They look similar to like family trees. And so like 6 is the child of 3. And there's a subtree rooted at 6 that has the nodes 4, 6, and 7 in it. So that's a subtree. And then 8 is what we call a root. And a tree has a root, and then a subtree, like the subtree rooted at 3, that has a root as well. One last piece of vocab, a node, so those are the circles, a node that doesn't have any children, that's going to be called a leaf. And you can see those are sort of at the bottom of the tree. Those are going to be leaves that don't have any other children. Okay, so we saw root, the node at the top of the tree. Subtree is a subset of the tree rooted at one node. Leaf is a node with no children. And then we're going to define the height of a tree as the number of edges on the longest path from root to a leaf. So here the tree shown has height 3. And you could imagine that we could have called this height 4, but we're just going to be consistent so that we don't have off by 1 errors and say it's going to be the number of edges on the longest path from the root to the leaf. Okay, and so imagine you just had a tree with a single node. That's going to have height 0. And maybe that's a little counterintuitive, but we're going to stay consistent here. Similarly, if you had an empty tree, we're going to call that a node with a height of -1. Okay, so these key properties of a binary search tree: every node has 0, 1, or 2 children. All children in their left subtree are smaller, all children in their right subtree are larger, and there are no duplicates allowed. And again, height we could have defined in a slightly different way to be 1 different, but we just need to be consistent. But this vocab that's on this slide and these key properties of a binary search tree are super important.